Spot on. Well, yeah, first and foremost, just thank you to Sanyo and the MFEM team for setting up and running the workshop today, and more broadly for your advocacy in making MFEM available to all. The work that we're going to kind of gallop through a little bit today is the result of the first 7 months of an ongoing Department of Energy Phase 1 SBIR project. And as the title at the top of the slide suggests, the objective of this project was to develop a GPU-accelerated, very high-performance and energy-efficient solver for highly compressible flows. We'll look forward to questions at the end, and we'll hopefully have time for those. But I did want to emphasize, as we sort of present and go through this early development work, we would love to hear from interested potential users or contributors, or even folks who just think this might be useful or applicable if it was extended or developed in a certain direction, as we don't want to develop this capability in a vacuum. So I'm sure that most on the call, and we've got a really diverse global audience today, most of you won't have heard of Synthetik, so let me just give you a very quick overview of who we are and what we do. And we're based in the United States and headquartered in Austin, Texas, where I'm talking to you from today. And we currently have a team distributed across the United States. And as the slide indicates, we really work at the intersection of applied research and development, modeling and simulation, and engineering consultancy, with the focus of today's briefing laying predominantly in that top circle with our M&S team, who develop codes, provide consultancy support, which is mainly, but not exclusively, in the domain of highly compressible reactive flows. And here is that aforementioned M&S team. So you'll hear from each of my friends and colleagues as part of this briefing, and Jeff, Ben, and Barlev have done much of the heavy lifting in terms of the code development that you'll see today during the Phase 1 SBIR. And in my opinion, they've done an outstanding job, but I'll let you decide that. And I also wanted to acknowledge Mac, who you can see on the slide here, who worked with us when he was finishing his PhD before moving to a postdoc role at Stanford. He did much of the early work on the blastFEM code to get us in a position to write the successful Phase 1 SBIR application. So here is a little bit of background and development history to set a bit of context to the briefing. Back in 2016, we developed a highly compressible flow solver that leveraged the OpenFOAM libraries, and we continued to extend and develop that code as an open source project. And earlier this year, we developed a stripped back GPU accelerated and optimized version of that was sort of back compatible. And that was under Dr. Jeff Heylmun, who you'll hear from later in the briefing. And finally, as a sort of natural progression of that work, we had a strong desire to work with MFEM in order to benefit from the higher order DG schemes, the GPU support, and the ability to run exascales, pretty much everything that you've heard today. And the development of that code, blastFEM, is the subject of today's briefing. So hopefully with that context and background set, this is the format that we're going to go through. Ben, Jeff, Peter, and Barlev will pick up different sections of part one and give you a break from my slightly monotone delivery. But essentially, the two parts you can see there is the format. And finally, Barlev will go through part two, which will be some of our initial Phase 1 results, and then any questions. But Ben, over to you.
Thanks, Tim. So first, we'll briefly cover some of the theory behind blastFEM's development, and then we'll look at some of the features that we've included. So blastFEM uses the compressible Euler transport equations. This is a system of hyperbolic nonlinear PDEs, and we use the discontinuous Galerkin formulation, which is an ideal setup for solving highly compressible flows where you have shocks or discontinuities. As a starting point for development, we used MFEM's example 18 code, which implements exactly this. It's the single phase Euler equations, which we show here using discontinuous Galerkin. Next slide, please. We then wanted to extend this to the two-phase Euler system by adding the transport equations for a volume fraction alpha and splitting the density transport into a partial density, one for each gas phase. And you can see what that looks like in these equations here. We then had to close the system of governing equations by adding an additional equation for the total density, rho, which we show there. And that's based on the partial densities and that volume fraction alpha. And finally, we add an additional equation of state, which relates the density, the pressure, and the energy. Next slide, please. So I mentioned the equations of state. So we've implemented a few different options, including the usual ideal gas equation of state, which I'm sure everyone's familiar with, as well as the stiffened gas equation of state and the van der Waals equations of state. And these are easily selectable by the user, and you can use different equations of state choices for different gases within the same simulation. And we can also easily extend this framework to include a wider selection of equations of state as needed. Next slide, please. Now, one of the more powerful tools we have at hand for improving the performance of blastFEM is the use of adaptive mesh refinement. That's already available within MFEM's capabilities. So we went ahead and used that so we can add refinement where we have regions of strong pressure or density gradients, and we can coarsen other regions. We can also easily use this AMR to refine near the initial conditions where you have strong gradients. So in this case, where we have an initial region of high pressure, we can refine around that to start with. Next slide, please. Thank you. So in addition to AMR, we can further improve our performance by leveraging MFEM's load balancing features when you're running in parallel. So here we show a comparison of a few different cases. We have uniform refinement on the left. We have AMR without load balancing for the same simulation setup. And you can see already with AMR and no load balancing, we have about a 3 times speed up. And then finally, we can introduce load balancing as well. And you can see the comparison between no AMR to AMR with load balancing, we have over a 5 times speed up. And so that's just a sort of low-hanging fruit for really improving the performance of blastFEM. This case here was a pretty simple case where we ran it on 12 CPUs with just first-order basis functions, but we can extend the size of this pretty easily as well. Next slide, please. One small change which we made was to improve the time stepping method. So rather than using the smallest element size and the largest velocity over the entire domain, we can look at each element independently. So we can grab that element size and we can look at the velocity inside that element and look at that ratio for all elements and use that to select our time step. And that just helps us to prevent from over constraining the time step, which you might run into with some cases. Next slide, please. So in some cases, in high order FEM with strong shocks and gradients, you can run into numerical instabilities. This can include oscillations or unphysical states where you have negative densities and pressures, or you can have poor interactions with boundary conditions. And we can help to mitigate this by the use of shock capturing limiters, which is where you place a limit on how much the solution can vary within the element, how much it varies from the average value within that element. And so we based this work on literature, and we are also able to provide the user with input to select how strong they want that limiter to be, or the user can disable the limiter as needed. Next slide, please. And in addition to the limiters, we have another option to improve the stability, which is artificial viscosity. So for high order FEMs, or for high order FEM schemes where you have shock fronts or discontinuities which you want to track, you also want to be able to resolve that shock within the element itself. And artificial viscosity helps to stabilize that sort of system. So for this, we followed literature as well. We used a method where we take our solution field, we project that solution down to a lower order field, and that gives us, and by taking the difference between those two fields, that gives us an indication of where you have strong gradients or discontinuities. Using that indicator, we can then apply viscosity to those regions of the domain. And that viscosity is based on the cell size and the basis order function, or the basis function order. So we show a couple images here. On the top figures, we show where the viscosity has been added. On the left, we have blastFEM results. And on the right, we have results from literature for the NACA airfoil at Mach 0.8. And you can see that we're adding viscosity in the correct regions of the domain. And on the bottom, you can see the pressure field, and we see very good agreement with blastFEM and literature. And this is for 4th order basis functions. So we're able to resolve those shocks within the interior of the element. Next slide, please. And with that, I will hand it over to Peter for looking at case creation.
Hey, thanks, Ben. So during the first phase of this program, and really as part of making MFEM more accessible to users modeling industrial flows more broadly, we wanted to quickly prototype a CAD integrated workflow. So as such, we adapted our SketchUp to GMesh extension for use with MFEM. This extension, it's available for free on the SketchUp extension warehouse, essentially converts 3D CAD geometries into valid GMesh grid generation input files. Conveniently, boundary names, desired element edge lengths, these can all be applied within SketchUp. We also developed an import utility to import an implied boundary and the initial conditions to the MFEM cases of interest that we're running. This capability, we hope, will provide utility to the MFEM user community, and it's one that we use to support much of our commercial work. So with that, Dr. Jeff Heylmun will walk you through some of the work that we've done creating rich input files and integration within MFEM.
Thanks, Peter. So in addition to the numerical schemes that Ben talked about, we also have had a large focus on simplifying and kind of generalizing the inputs for arbitrary case creation. So this is a sample input, and it's broken down into a couple different sections. So we have our controls, our mesh schemes, phases, and initial conditions. So the control section controls things like the end time, the write interval, and visualization method. These would typically be put in through command line. For mesh generation, we focus primarily on Gmesh. So if that's used, you can construct your mesh using named boundaries, which can then be used to specify boundary conditions by name. This is also where order and adaptive mesh refinement procedures are specified. Next, we have, you can see the specification of the flux schemes as well as the ODE solvers and the limiting coefficients. For the phases, this is going to be a two-phase simulation. So we have the first phase, which is going to be an ideal gas, and the second phase, which is stiffened gas. And you can see the parameters specified for both of those. And then finally, we have our initial conditions, which is a combination of an initial uniform or default value for all the fields, and then a selection of simple shapes like spheres, cylinders, or rectangles for different fields. And with that, Barlev will now show some results.
Thank you, Jeff. So with the work developed and as described by my colleagues, I'm going to walk you through some of the results that we've gotten with our development work. So first, single phase results. The simulation on the left is an external flow over an arbitrary geometry that was meshed in Gmesh and then imported to be used with our solver. So the flow here is about Mach 2.5. We have a velocity inlet boundary condition at the bottom there, and outflow extrapolated boundary conditions on either side and on the top, and of course a wall boundary condition for the geometry in question. This was done with the second order basis function and AMR with load balancing. So you can see that adaptive mesh refinement resolved the shocks in that case. On the right, we have a box essentially with a circular obstruction. So all boundaries here are set with the wall boundary conditions, no penetration. And we've initialized the center with a high pressure in the domain. And you can see that the shock is caused because of that pressure normalization. So what we're showing here is a fourth order solution on a coarse grid by controlling the limiting that Ben talked about using the limiters that we've implemented. So you can see there's no AMR, and you can see that that shock is well resolved. Moving on to the next slide. We've done some validation of the single phase code that we have. So the result on the right is a shock tube that's 100 meters long. And this configuration begins with equally partitioned regions of high pressure and density on the left and low pressure and density on the right. So as we run this case out, the shock traverses to the right, and there's a rarefaction wave that revolves on the left. So what this picture shows here is a comparison of the simulated result and an exact solution. So you can see that it's pretty spot on. We've also done some validation with the NACA 0012 airfoil geometry under transonic flow conditions. So you can see that shock that's formed on the top surface of that airfoil. We've computed the coefficient of pressure on both surfaces and compared it to the literature. And you can see that it's a pretty comparable result, especially that location of and strength of the shock there is consistent with our findings. Moving on to the last main result, which is two-phase. It's a two-phase system. Here we have two fluids, the fluid with a higher density, and pressure is set at the center there. So that we're looking at a pressure ratio about 20:1 and a density ratio of the fluids about 2:1. So here we're showing the fields in question. You have a volume fraction field on the top left there. We have the transported masses tau for O's and the total density on the right. With the bottom row, we have pressure, the energy, and velocity magnitude. So both phases here use the ideal gas equation of state. We've done the simulation with AMR. and load balancing, as you can see the bottom left animation there. And what I want to point out here is that the top and the bottom boundaries have no penetration. They're wall boundary conditions, and we have an outflow boundary condition on either side. So as that pressure normalizes, fluid 2, which is surrounding that central fluid 1, is pushed out, and the pressure waves reflect on the top two walls. The top and the bottom walls. And as it comes back, it compresses that fluid 1, moving it outwards to either side. So to sum up, we have an early development of a framework that handles single-phase and two-phase system of Euler equations for highly compressible flows. So we've leveraged MFEM's utilities such as the AMR and load balancing, and we've implemented methods for shock capturing. We've also put it all together and implemented a pre-processing utility which would help a user set up a simulation with ease. We'd love to hear from the viewers and potential users or contributors with any feedback. And with that, we'll take any questions. Thank you.
All right, thank you very much, guys. Thank you for the really impressive talk and for staying on time. That was 4 people, very impressive. All right, questions for the Synthetik. So I have one. The SketchUp plugin, so did I understand correctly that it produces a Gmesh input file and then you generate the mesh from Gmesh?
Hi, Sonia. Yeah, that's right. So I don't know if anybody's ever used SketchUp before, but I think they still maintain a free version, but it's either free or extremely cheap, pretty easy to use, quick kind of 3D CAD modeling tool. This plugin is one that we developed some time ago, and then really just kind of verified and ensured that, yes, it still continues to work with the latest version of Gmesh, and then with the work that Jeff has done, that we can complete that workflow from quickly sketching some 3D CAD geometry within SketchUp. With this utility, you can apply boundary conditions effectively, so you can name the different faces of your CAD geometry in accordance with what kind of boundary you want to set. You could do some multi-region grids as well. So if you had one, if you imagine we're doing a solids type problem, and I don't know, we had steel and rubber together, and you wanted to kind of model those separately, you can name those volumetric regions as well, and those will be respected in the Gmesh input file that gets generated. So at the end of all of that, you can simply save a .geo file, which is what Gmesh takes in that format. You can generate grids then using that as your starting point from Gmesh, and then if you save that and load it in, you will see those physical groups, which is what the sort of Gmesh syntax for naming different particular regions or boundaries respected, and you can then take that and import that within MFEM, and you'll be able to apply boundary conditions to those particular faces.
Thank you. Okay, other questions? Okay, let me ask one more. For the adaptive mesh refinement, did you use just the ZZ error estimator, or did you do something different and special in your case?
So we actually used, it really looks at the phase difference of a given field. So we usually either look at density or pressure, and we just look at the values across a face.
Thanks. And well, last question. Did you guys is this all on CPUs? Did you guys get a chance to try any of the GPU capabilities in MFEM?
So this is all currently on CPU. Sano, as I say, it's first 7 months, so we're going to obviously look to go to GPU, but yeah, this is all CPU, everything that we presented today.
Thank you very much for coming and sharing. This was very interesting.
Yeah, it's impressive work.